Hello again, grade 8s. In today's math lesson, we are going to wrap up the unit on probability by distinguishing between theoretical probability and what actually happens experimentally when you perform a probability experiment, which is referred to as experimental probability. Okay, so we're going to distinguish the two, theoretical and experimental probability. Theoretical probability is the calculated probability of an event occurring. Every single calculation we have done in this unit up to this point has been a theoretical calculation. Okay, we're predicting like the likelihood or chance of something occurring before actually even performing the experiment itself. So for example, if we had a six-sided die and it was rolled, and I want to know the theoretical probability of rolling at least a 5, well, first of all, let's identify what that means. So let's pull up my pen here. So my sample space for the six-sided die would be you could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, or you could roll a 6. Now, at least a 5 means that it is a number that the smallest allowable number would be a 5. So that's greater than or equal to 5. So that'd be 5, and 6 would be allowed. So if we performed a calculation for this, the probability of obtaining a number that is at least a 5 is the same thing as calculating the probability of getting a number that is greater than or equal to 5. That would be equal to your favorable outcomes divided by your possible outcomes, which would be you have 6 possible outcomes. 2 of them are favorable, greater than or equal to 5. So that'd be 2 over 6, which would give you a decimal of 0.333 if you round it correctly. And then if you turn it into a percentage, you would get 33.3%. Now, experimental probability, on the other hand, is the probability of an event occurring based on actual or experimental results. So what it means now is you're actually going to physically start to like flip the coin and see what happens. Maybe a good example of this would be like, theoretically speaking, if I told you to take a coin and flip it 10 times, it could be like any coin, theoretically, we should get heads 5 times and we should get tails 5 times. Theoretically, that's what should happen. However, if you flip a coin 10 times, you might get tails 3 times and heads 7 times. So that's what actually happened. So your actual experimental results are a little bit different from what happens in theory. And that's what experimental probability is all about. To determine experimental probability, you have to base the outcome on repeated trials. So it just means that you have to perform the experiment over and over and over and over and over again to collect a bunch of data. We can calculate it using the following equation. So we're going to write down P, and then we'll write down a subscript that is EXP. So the EXP stands for experimental probability. And this would be equal to the number of times you obtain a result that is desired, or I said the number of times a desired result is obtained, divide by the total number of times you actually perform the experiment. So I'm going to take this and just abbreviate it with an acronym, which is going to look kind of silly, actually. So for the numerator of the equation here, the number of times a desired result is actually obtained would be DRO. And then this is divided by the total number of trials of the experiment. So I just abbreviated total with TOT. Okay, just right here. So it's a bit of a different way that we're actually going to calculate it, because for experimental probability, we actually have to observe how many times I got my desired result and then divide that by the total number of times I actually performed the experiment. Okay, so the numbers are not going to be the same as if you did a theoretical probability calculation. Okay, let's look at an example of this. So it says a six-sided die is rolled 12 times, and then the actual outcomes are shown in the table below. So it says calculate the experimental probability of rolling at least a 5. Okay, now I just want to point out again, theoretically, we just did this calculation. So we said the theoretical probability of obtaining at least a 5 should be 33.3%. Okay, in theory, that's what I should get. Now, I actually did this. I took a 6-sided die, I rolled it 12 times, and I recorded all the different results I got. Okay, and this is what I obtained. Okay, so I performed this experiment 12 times, and I've recorded the frequency in which I obtained that result. So this is a tally chart. So each one of these ticks means that's how many times you got that number on the die. Just be aware on a tally chart, if you start to get up to a 5, so like you would have like 1, 2, 3, 4, and the 5 represents a horizontal line that goes across it. Okay, so just if you're interpreting a tally chart later, that would actually represent 5. We don't need to worry about that right now. Okay, so when I did this, I rolled the die 12 times. I got a 1 4 times. I got a 2 2 times. I got a 3 once. I got a 4 3 times. I didn't get a 5 at all after rolling it 12 times. And I got a 6 twice. Okay, so let's see what our experimental probability is. So the experimental probability of obtaining a number that is at least a 5, which is greater than or equal to 5, would be equal to the desired result that is obtained divided by the total number of times I performed the experiment. Okay, so how many times did I perform the experiment? So that's TOT. Well, it says right up here I did it 12 times, okay? I rolled the die 12 times. DRO, how many times did you actually get this? Did I actually get a number that was greater than or equal to 5? Well, I only got it twice, okay? I didn't get a 5 at all, and I only got a 6 twice. So this would be 2 divided by 12. So the 12 times I actually performed the experiment, I only got my desired result twice. If I turn this to a decimal, this is a repeating decimal, by the way. If you round it correctly, it'd be 0.16. Turn it into a percentage, it'd be 16.7%. So I want you to note the difference here. So let's just kind of compare this. So experimentally, this was the probability of me obtaining a number that was at least a 5. Theoretically, this is what I should have got, okay? Theoretically, what it tells me is 33% of the time, I should have got a number that was at least a 5. But when I did it experimentally, I only got that number greater than or equal to 5, 16.7% of the time. So really what I'm trying to point out here is that our results that are predicted in theory do not always match up with what happens experimentally. And again, that's why we're doing this separate calculation here for our experimental probability. Now, I should point out that if you start to do this experiment a lot, like if I took that die and I rolled it like 5,000 times, you're going to find that as you start to do the experiment over and over and over again, that your experimental probability does start to get closer to what happens in theory. In statistics, we refer to this as like we need like a large sample size, which means we need to like conduct an experiment a lot to get like meaningful data. I mean, just rolling this die 12 times would not have been like an effective sample size. So if I did perform this experiment like 5,000 times and then did my experimental calculation, I guarantee you my experimental probability would have been a lot closer to 33.3%. Okay. But I'm not insane and I don't want to, actually that's up for debate whether or not I'm insane or not. But I don't want to waste my time by rolling a die 5,000 times and then constructing a frequency table. So I just did it 12 times. Okay, let's look at another example. Example 2. So it says a coin is flipped twice, and this process is repeated over multiple trials. The results of the consecutive coin flips is shown in the table below. A says, without constructing a table or a tree diagram, calculate the theoretical probability of obtaining tails on flip number 1 and heads on flip number 2. Okay, so we're just going to do a flat out theoretical calculation. Okay, so we don't need to worry about the data collected in the table for doing a theoretical calculation. The data collected in the table is only useful for our experimental calculation. And once again, writing at the top of the page pulls up that weird icon thing. Okay, so we're flipping a coin twice. So if I flip a coin once, so we'll say flip number 1. Okay, flip number 1. There's 2 possible outcomes. So the sample space would be you could obtain heads or you could obtain tails. Flip number 2. Flip the coin again. And again, your sample space would be heads and then tails. Now, I theoretically want to calculate what's a probability of obtaining, what did I want? Tails on flip 1 and heads on flip 2. Tails on flip 1, heads on flip number 2. Okay, now, I could draw, this would be a really, really easy table or tree diagram to draw, but I'm going to use the multiplication method to do this. So the probability of obtaining tails and then heads would be the probability of obtaining tails on flip number 1 times the probability of obtaining heads on flip number 2. Okay, so this would be equal to, okay, on flip number 1, how many possible outcomes are there? There's 2. You can get heads or tails. On flip number 1, so again, just to clarify this is flip number 1. This is flip number 2. On flip number 1, how many ways can I obtain heads? Well, tails? Just once. Okay. Multiply that by the probability of obtaining heads on flip number 2. Well, on flip number 2, there's 2 possible outcomes. You can get heads or tails. And how many ways can you get heads? Well, there's just one way. Okay, so this would be equal to multiply. Numerator times numerator is 1. Denominator times denominator would be 4. Turn that into a decimal and it'd be 0.25. And then this would be equal to 25%. Okay, so that's how we would do that calculation theoretically. You could have also, again, done a table or a tree diagram and then done the calculation for both independent events together. But again, I just want to do the multiplication method here just to reinforce it. Okay, now B says determine the total number of trials that have been performed. Okay, so my experiment involves flipping one coin and then flipping another one. And it tells me how many times I got these different combinations. So all we need to do is to figure out how many total trials were performed is I'm going to take all these numbers in the table here and I'm going to add them all together. Okay, that's going to tell me how many total times the experiment has been performed. So we're going to use the acronym TOT for that. So TOT would be 125 plus 130 plus 140 plus 135, and then the total number of times that this experiment was performed, where you flipped a coin twice, would have been 530. Okay, now C wants me to, what's the experimental probability of getting tails on flip 1 and heads on flip 2? Okay, so we're going to write down P, and I'll write down that subscript EXP to indicate I'm calculating experimental probability. So experimental probability of getting tails on flip 1 and heads on flip 2. So that's going to be equal to the number of times your desirable result was obtained divided by the total number of times the experiment was performed. Okay, so how many times did we perform the experiment? Actually, so again, experimental probability is what you actually then perform the experiment. You start flipping the coins and see what your results are. So we did this 530 times. Well, I shouldn't say we did it. Somebody else did it. No, I did not flip these coins 530 times. Okay, now how many times? So this DRO means desired result obtained. So how many times did you get tails followed by heads? Well, that's this right here. Tails followed by heads, when I actually did this, we got 140. Okay. So again, to do an experimental calculation, you actually need to perform the experiment, do it repeated times, and then kind of record how many times you got all the different outcomes. Okay, now we're going to calculate this. So 140 divided by 530 would be a repeating decimal. I know it's a repeating, but it's I don't know if it has a repeating pattern to it. But anyways, it's an ugly decimal, 0.26415. ... I don't know if the pattern starts to repeat then or not. And again, we want to round this. So nearest thousandth. Let's look at the first 3 decimal places, and we look at the 4th digit to identify if we round up or not. Since the 4th digit is a 1, we don't round. That would just stay at 0.264. So this would then be is equal to 0.264. And then this is turning into a percentage multiplied by 100. You have 26.4%. Okay. Now, I just wanted to point something out here. So remember what I said? I said, like, the more times you actually perform an experiment, the closer the experimental and value is going to get to the theoretical one. Well, look how many times we did this experiment. 530 times. 530 times, I got tails followed by heads 26.4% of the time. Theoretically, I was supposed to get that 25% of the time. Now, there's a much smaller gap between those numbers. The difference between 25% and 26.4% is only 1.4%. So by doing it a lot of times, I actually started to get my experimental probability closer to what it should be in theory, as opposed to over here, we only did it 12 times, and my experimental probability was actually like half of what it should have been theoretically. Okay, so just an interesting thing to note about statistics is, again, like, meaningful data comes when you do perform an experiment a lot of times. You need lots of like collected data points. All right, so that's it for this lesson and this unit, actually. And you can complete the probability work booklet by completing the assignment called experimental probability. And then I will talk to you in the next unit of study.